How's everyone doing? Boston? Yeah. Class is atrophying. Well, we do have an observing night tonight. I think we will have it. Weather looks good for once, even though it was windy earlier and they did not replace the domes, which I'm upset about. But I'm not gonna be able to do anything about that. We're gonna try to get up there and get started in year 6. I know some people said that they had to leave early because they have class. So if you're up there and you just want to check it out and see some stuff, show it right away. Question before we get started? Yeah.
Will the observatory also be
6 to an indefinite time period. We usually go until people stop showing up. Yeah, you can always have Slack if we're still there. Okay. What's this? What's that? A planet, good. One of our planets?
Yeah.
Yeah? Which planet? Venus, okay. So you're saying like it's really close to the sun? You're thinking it's gotta be Venus, right? This is an artist rendition of a planet outside of our solar system. So we're gonna start talking about this today and probably on Tuesday. We'll do exoplanets, planets outside of our solar system. But to wrap up what we talked about before, of course, I found something just on Twitter from JWST, brand new observation. What's this? What's that? Supernova, that's a very good guess. 2 guesses there. So either it's an exploding star or a star being born, and it's the latter here. So this one here is a star being born. You're thinking to yourself, what am I really looking at? So let's turn these off for 1 second. How do I turn these off? Okay. Better colors, right? So this part here is very dark. Why is it dark there? There's a lot of dust. Okay, I can't see through the dust. You can see some stars, really bright stars, faint behind them. So there's a bunch of dust here we can't see. What we do see is these pieces here, which are like cones that are being blown out. Okay, and somewhere in the middle here is a brand new solar system. Okay, so you zoom in on that tiny piece there, you can actually see the edge of the disk, and the star is just inside there. Right now, that star is not doing what our sun does, which is to turn hydrogen into helium. It hasn't started that process. And this material here is forming in a disk, just like we thought it would. So this is young. You want to guess how old this is? Just guess when I say young, cosmically. 100 million years. Bigger or smaller? Bigger? Smaller? Smaller. This is 100,000 years old. This is younger than humans, which is pretty remarkable. So this is as brand new as I've ever seen. And the structure here is absolutely fantastic. So these are like pieces of gas which are being blown out. The size here is the size of the solar system. The whole solar system is going to shrink down. This whole thing is going to shrink down to about that size. That make sense? Okay, another cool, no? No or yes? No, okay. All right, I'll put this on the bottom. Just this picture. Okay, so what's this? See if I can make it go. Yes, let's go. Now this is like an hour and 45 minutes long, so we're not going to watch the whole thing. Where'd it go? Let me see if we can get. Okay.
Back to T-minus 10 minutes and recharge those batteries.
Okay, hold on. I guess I should have figured out exactly where it was, and there we go. Okay, let's go back. Okay, has anyone here seen a rocket launch? No. Just this one. So this one's important. This one is on what's called the Space Launch System. So this will, is it flying?
It is one.
Yeah, it is. Okay, so this thing is absolutely massive. When you start to think about how tall it is, just think bigger. So this is ignition. They shoot these sparks up here. They put water down. Oh, we have to, I guess, listen to it. Damn it. Stop. Okay, let's take one step back so I can talk about it and then we'll watch it. So this is an uncrewed mission, but this is part of the Artemis space mission, which is going to send human beings back to the moon. And in order to do that, they're going to sit right up there. And all of this is fuel all the way down. The hundreds of, like, imagine you're sitting on the top of a 20-story building and everything below you is fuel. So they're going to ignite it. It's going to be hot and loud. They're going to press it out the bottom in order to go up. These little ones on the side, they'll fall off too. It's not a very good video. I don't know why they decided to do it at night. Yeah.
I was gonna ask about it. Water.
At the very end, what you're about to see, yeah. So they're gonna pour water to make sure nothing catches on fire. So that sparking that you see at the bottom, right? That's not at full ignition. So we have to start it a little bit. But actually, man, I wish they had a better view. So at the bottom here, they have a concrete thing that this is standing on. And it basically just has like an enormous pile of water that's gonna get vaporized. If it didn't happen that way, all that fire that goes down would then melt the concrete and they wouldn't be able to fly again. It's very hot, obviously, it's fire. Okay, cool, you wanna watch, just 5 seconds maybe? All right.
Voyage to the moon. Launch team can no longer recycle the count. Sound suppressor water now flowing
15.
under the ML. And here we go.
10.
Hydrogen burn off igniters initiator. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
Five engines on the core stage and 2 solid rocket boosters now propelling the vehicle at 128 miles per hour.
Like,
Carrying good control on the roll from teams in Mission Control Houston. All good calls so far. Now 30 seconds into the flight Artemis 1. First milestone will be for the vehicle to pass through max Q in about 1 minute and 9 seconds into launch. This is the greatest period of atmospheric force on the rocket.
so you think I didn't do my homework? Come on now. You know me better. Okay, so there's the picture. Oh, wait 1 second. Okay, so there is a long exposure picture. So I just want to show you the scale again. Okay. So like everyone you ever known lives like right here, right? Very, very short part of the earth. And this is what happens when you go up into space. Fine. I want that one. What about this one? That's pretty cool. That's pretty cool, right? Yeah. If you have the opportunity, I would recommend Vandenberg Air Force Base. So you can go online, and maybe I'll link this in the course modules. You can just find out when there's a launch, and you can go watch one. And if you live closer to LA, or if you live like even just looking in that direction, you'll see them come from what looks like north of Malibu. And so you want to look for like a sunset launch. Okay, and then this one's so cool just because it's sort of illuminating how hot this is. Why is it so light? Why is there light coming from here? Why does fire give off light? Because it's hot, correct. Very good. Okay. So we're gonna have to, oh, sorry guys. Should have warned you. We're gonna have to warm those brains up again because we're gonna learn about light today. And so, right? Ready for light? Questions about this? What's it doing? This one is cursed. Okay. Okay, so which of the following is not a method used to detect planets around nearby stars? Is it the astrometric technique, the radar technique, the Doppler shift technique, the transit method, or direct imaging? Let me know when you're ready to vote. Vote on 3, 2, 1. Okay, all right. All right, so let's talk about other planetary systems. We've talked about terrestrial planets, talked about Jovian planets. We're going to talk about these other stars. Why is it difficult to detect stars and other planets? Because of the light. What about their light? Okay. So they also produce a little bit of visible light. That's good. But there's a bigger problem. They're too far away. Okay, this is my biggest problem. Right, if they're close, then you can see them better. And we see Jupiter good because it's very close to us. Okay. So there's 2 ways to do it. You can directly look at it, take a picture. So for example, this one here, this is an example of direct or indirect detection. What's that? This is direct because I can see it. It's right there. Right. So if I can see it, that's called direct detection. If I can take a spectrum of it, that's direct detection. There's other ways where we have to sort of guess. We have to infer the properties based on what we already know. Okay, those are indirect methods. Okay. And we already talked about why direct detection is so hard. Let's think about it in the right context. So we were talking very, very early on in the semester about if we're going to put the solar system at the right distances, right? You took the sun, you made it the size of a grapefruit, you put it here. Where's the Earth? Is it in the room? Oh, 40 or 50 feet away. So you can't do that. Okay, that's fine. And then where's Pluto? Look at the observatory. Our whole solar system at that scale fits like basically on campus, right? And the nearest star at that scale? On campus? Well, no, thankfully. We'd be in trouble. In LA? Farther, you do like more or less distance? Can you tell me? Less distance? You think it's closer?
Maybe like Riverside.
Riverside? Anyone else? Everyone agrees Riverside. No, what's your, you say LA? Okay, both LA? Anyone higher, bigger, smaller? No, false. It's New York City. The nearest star at that scale is New York City. And there's no other stars in between. So it's just empty. So imagine for a moment, we have our grapefruit, our orange, stick it here. We stick a different grapefruit or orange in New York City. Okay, and now how big was a planet on that scale? Say even a grape. What was the grape supposed to represent? I know this is so long ago and I don't have the food here, so it's not as good. We're doing a scale model solar system. Grape was Jupiter. Jupiter, good. Okay, so we have a grape and a grapefruit that are in New York City. And we're going to try and see them from here. Easy to do or not? No. No, hard. Okay, so this is why finding planets around other solar systems is hard. Okay. Did I say that right? Mostly. So you have to light it on fire. Right, because obviously it's dark in this fake world that I created. But the problem is, and this is the hardest part. If you think about that grapefruit that's burning, it's lighting itself up. So that you can see it from here. It's going to be about 1 billion times brighter than the light that bounces off of the surface of the planet. So taking a picture of it is hard, right? Make sense? Okay. I'm gonna really brush off some of those older thoughts here. So, at what wavelength would it be easiest to see the planets emitted light? I just said here that this is the difference. It's about 1 billion times brighter in the visible. And now I'm saying which of these wavelengths would be easiest to see the emitted light, emitted, not reflected. Is it X-rays, ultraviolet, visible, infrared, or radio? Show me your fist when you're ready. Let's vote on 3, 2, 1. Okay, all right, a lot of people pick the same one. Is it X-rays? No, what are X-rays? Where do those come from? They come from stars, yes, that's true. They're very energetic, right? That's why they go through our body and let us see inside, right? Do planets emit X-rays? No. Yeah, that's the important one. So what about ultraviolet? No. Why not? They don't emit ultraviolet light, right? Definitely not from the surface. Visible? So planets emitting visible light, is that a good thing? No. No, because it's very hot. Okay, it's too hot if it's emitting visible light. I mean, some people are interested in planets like that. I'm not personally. Okay, so we're left with 2 options. Good. And a lot of people picked one of these 2. You don't want to defend their choice. Yeah.
Picking the reference, like our own planet gives off infrared light.
Okay, so our own planet gives off infrared light. Right. Yeah. Yeah, and that's correct. So it turns out if I write it this way, so this is wavelength, over here is the ultraviolet, here's the visible where we see, and here's infrared. And you look at, this is the total energy, how much light is being given off. The sun is this top one. It gives off all the light. And here you have a reflection off of the earth. But over here on the right-hand side, this is the emission from the planet. And it peaks in the infrared. And notice on this side, this distance is small compared to this one. What does that mean? It means if I take the top and I divide it by the bottom, it's a bigger number. They're farther away. This is 1 and this is 100. And I divide them and they're 100 times different. They're close or even the same. It'd be great. Right? Make sense? Okay. So if we do direct detection, we try to do it in the infrared. That's the easiest place to do it. So that was this is Fomalhaut B. As we mentioned before, you have to sort of block out sun. It's not the sun, it's Fomalhaut. And the planet's name is Fomalhaut B. You run out of good names really quickly when you're talking about exoplanets, because you can't just keep naming them after fun things. We literally run out of names. So over here on the right-hand side, I don't remember who that is, but you can see that there are multiple planets being directly imaged. And you can even watch them go around. So we name these in the order that we find them. I don't know why. So you have B, C, D, and E here. And then we think there's probably not another one closer. This is an example of what that would look like. Bright star, dim planet, hard to do. Okay. Okay, so a majority of planets are not found this way. So how do we find planets? Okay. You can see a planet's there by seeing what it does. Okay. What are the different ways that a planet could influence something nearby that I could see? What is nearby that I can see to the planet? We mostly only see the star. Right? It's basically so far away that the only thing that matters is the star. Okay, so what could it do to the star? If you have a very massive planet, okay, then while the planet is orbiting the star also orbits the planet. We saw that for example, Pluto and Charon, its moons, they're actually going around each other like that. So if you had a supermassive star, like very large, and then you also had a very massive planet, maybe they would go around each other too. And while I can't see the planet, I might see the star moving around, right? Wobbling. Okay, that's the primary way we're going to see this. Another way we're going to see this is, let's say I have the star, and it's like one of these. Have you ever been walking around and you see like a shadow pass over you really quickly? And you look up and it's a bird or I was gonna say plane, but yeah. Okay, so something has passed over you. So what happened? Something moved in between you and the sun, right? Well, what if the planet does that? And you're watching the star, right? What would happen? You see the planet go in front of you, the star would look like it got dimmer for a second, right? Okay, so we can still kind of tell that planets are there. All right, and we're gonna talk about those. So that's the transit technique, passing in front of something. So that you can think plane or bird here. And then these ones are the wobbles. So these are the ones that pull because it's massive. Okay, and it's going to make the star not go straight and make it go like that. Cool. Okay. This one we'll talk about very little. It's called the astrometric technique. So what we do is we watch something for a really, really long time. So starting in 1960, it looks like it's over here. And then if you follow this and you do it really well, you see over here 1980, 1985. And as it goes around, it's sort of wobbling. And we can't see why it's wobbling, but we can infer that there must be a massive planet that's pulling it around. Okay. This is really hard to do. Okay. So notice what these numbers are here. That's 5 10,000ths. Okay. And if you notice this word here, it's the radius of the sun. So if I put this scale up to scale, right, this is like wobbling, not much larger than the radius of the sun itself. So it's really just doing this, right? To make this observation, you have to multiply these together, but an arc second here, just for like, if you think about that word, you don't know what that means. The distance of how far away something is on the sky. Okay, so a degree, you might have heard before, like 10 degrees from the horizon. And then if you divide that by 60, you get an arc minute. And if you divide that by 60, you get an arc second. Okay. And the width there is about a human hair from 30 feet away. So these are tiny, tiny imperceptible motions on the sky. They do nothing, right? Okay. Okay, that's it. You're not going to learn about astrometric. We're going to learn about Doppler. This one is far cooler. This one you're probably familiar with. What am I about to show? What's that?
Cars whistling by.
Yeah, cars whizzing by. Why do cars whiz by? Speed, yeah, so moving quickly. Am I currently experiencing a Doppler shift moving back and forth?
No.
No?
Yeah.
I could if I went a little faster, right? Okay, so we'll talk about why this exists. So first, the example. Has anyone been to a race like this? Yeah. Yeah, okay. I wasn't sure if that was a question. Okay. All right, sounds fun. To describe that sound, what were you hearing? Okay, pew pew, is that correct?
No.
No, there's two parts to the sound, and we can listen to it a few times. What? Neom. Okay, neom. What does neom sound like? Now, what does a car normally sound like?
Doesn't make sense.
Car doesn't make sounds?
No.
Okay.
Sound or something.
False. it like hums, right? It goes right? Okay. So what did it end up sounding? Go ahead. No? Yeah, it sounds like well, they're definitely sliding towards us, right? Yeah.
I don't know if like little toy cars, you have to pull it back and it makes that weird noise.
Okay. These are moving slightly faster, so the difference in the sound there is because these are moving very close to how fast sound moves. So the reason that it's not happening to me as I walk around is because I'm hopefully not moving at 60, 90 miles an hour, right? They're moving 200 miles an hour. And so what you're actually hearing is the sound is being compressed as it moves towards you. Every sound wave that's given off is pushed because it's catching up to the one in front of it. And it turns out we hear that as a meow. So the first part is no, this is important. It's a high pitched noise. Okay, when they're close together, the pitch is higher. And when they're far enough away, the pitch is lower. Right? This is actually how it works. Okay. So that's sound. And my argument is that light does this. You believe me? Yeah. Okay. So it turns out that this is exactly what happens with light, but we also don't see it on a day-to-day basis. As I walk towards you, you don't see that my face is bluer. Instead, I'm not moving anywhere close to the speed of light. But if I were, or moving quite rapidly, say 500 kilometers per second, you would see things change their color very slightly. Okay. So here, as it moves towards you, all of these wave fronts, the different crests get close together. Remember that light is a wave. And we consider when they're close together that they're higher frequency and that they're closer to blue. Right? We keep going past blue, you get ultraviolet. Keep going past ultraviolet, you get X-ray. Short wavelengths, small distances between peaks are bluer. Okay. On the other side, as you go away, each one of these fronts gets farther away. Now it's a longer wavelength. Example of longer wavelength light. What's that? Red. Good, it's right up there. Red, and also past red. What's past red? I keep going. Whatever. Okay, on this side I have blue, this side I have red. If I keep going, but on that side I went towards ultraviolet, went to X-ray. If I keep making these longer and longer wavelengths, radio. Right, we talked about infrared, radio. That's another thing. Right? Microwave, the stuff that doesn't kill us. Okay. So this happens in the lab. So for example, we have these lines. You remember that we did this? Okay. dust off all of this. So if you have a question, let me know. I can walk any of this back. Okay. So these are the, for example, if this was hydrogen, these are the different places where hydrogen can absorb or get rid of energy. And it only does it at a very specific location. Okay, so it shows up here, here, and here. And I measured in a lab, it's not moving, and I look at it and I go, oh, great. But then I put it on a cart and I send it away from me at 500 kilometers per second. And I look at it again, and it moves towards the red. Here's what it was earlier, and it moves towards the red. All the reds get redder. This blue gets green. If it's coming towards me at 500 kilometers per second, then I see everything get bluer. So this blue becomes purple, and this red becomes orange. Okay, so I'll stop there for a second. Does that make sense? I see some people, yes, some people very quizzical. Like what? Witchcraft? Okay, let's see if you can do it. Ready? Which object is moving away the fastest? Let me know when you're ready to vote. Your fist. Let's vote on 3, 2, 1. Okay, all right, pretty good, pretty good. Of the people who answered, most people answered correctly. It'll be this one here. Okay, so this is moving away from us. Okay, away from us means red, or this means blue. Now, what I didn't tell you is what makes the shift move. Okay, I said the fastest. So you have two options. And I think some people put together, well, if it's moving away very slowly, maybe I won't see it. But if it's moving very quickly, it has a stronger effect. And that's certainly true. So how much it moves, tell us how quickly it's moving. And the direction comes from the color. So red means it's away. Red far means it's away quickly. Okay. Here's another example. I guess I just said that. That's the same thing, right? One last part. You can use this analogy. That's all I have is analogies. So red lights on the freeway going away from you. Okay? Unless you're touching. Don't think about that. So an analogy doesn't work well. Okay, but red lights going away from you, white lights towards us. Okay. Okay. So we're not going to do the whole thing here because it's a long one, but let's try and do the first two parts. Is that reasonable? We'll do the rest on Tuesday. Mind taking one, passing it back.
Yeah.
It was like yeah, and I'll ask about that one. Everyone see one? Do we have extra?
It's super.
Moving away, moving away is where. Moving away is where. So it's okay. When the situation you consider people that are not.
It's not even,
No.
so you don't have to carry that. Yeah, and it says it's gonna be partly cloudy at 7. I'm being so serious, dude. What's I mean? It is. Sheila went out to eat. So dramatic. I was.
Perfectly clear.
And that's 6 on the weather app. That's why I was after.
Whether it be.
The iPhone one?
Yeah, it's hard to say with that.
Like even there's even a cloud.
Yeah.
No traffic. The fun thing. So.
I mean, more comes. So, yeah, honestly.
I really, I don't wanna go. Maybe it's not gonna go, it's either rainy. It's too windy.
Best time was like early in the semester.
No.
Often.
If it does, and I couldn't skip.
Okay, so next time I teach it, I'm gonna have like 7 right in a row. Like at the beginning.
Yeah. One just week.
1 week. 2.
Yeah.
One on Monday, one on Thursday.
Yeah, but each week. For the whole month, have one.
Yeah,
So have one for the 4 weeks, have 2.
I have 18.
18. That's like the whole month.
I haven't decided when I'm getting it out. I guess we'll talk about that right before Thanksgiving. What? Yeah, not having a whole week is so strange.
I said we could change the last day. We have the whole week off.
It doesn't make any sense to me, like we get off like 1 day into December, and I'm like, I'm not happy to take 6 weeks, don't get me wrong. What did I say? Yeah, part 2, definitely, but not necessarily part 3, up to the end of part 2. Do part 2, yeah, sorry. Confusing. Was that clear to everyone? Do part 2, but not part 3? Oh. My bad.
Yeah, but I'm done. Of course, I'm done.
Yeah. I'm glad you did.
Yeah, I get traumatized. Anytime I see it, I'm like, oh, please put it on me on the midterm. So fun.
Oh, that's good. Good design.
I know, but I don't think it should get any out of it.
Okay.
I might, I did okay, better than I was expecting. Honestly. I don't want to ruin your plan.
I had to break you.
Yeah. Yes. 27.
Yeah.
I thought it
How are we doing? Couple more seconds? Couple more, like 10, 15 seconds? I mean, it's not to do with content. Yeah.
so sad. If I
Clowns?
wow. Fits.
Oh, no. I mean, how many?
Like if it looks like dust.
Yeah. What I always see is you can see stars. You can see stars.
Yeah, you have lights on too.
Okay, folks, let's see if we can use this. Yeah, between 6 and 6:30. Okay, let's see if we can use all of these things that we've learned. Suppose you found a star. Oh, she did a lot of work. Suppose you found a star with the same mass as the sun, with spectral lines that are slightly shifted red and then blue, with a repeating pattern of 16 months. What could you conclude? A, it has a planet orbiting at less than 1 AU. It is a planet orbiting at greater than 1 AU. The planet is much more massive than the Earth. The planet is much less massive than the Earth. We don't have enough information to know the planet's orbit or mass. Let me know when you're ready to vote. Let's vote on 3, 2, 1. I got a lot of non-voters. No one, okay, no voting. Okay, all right. Here's the question. What are we talking about? What's that? A planet. Okay, it's something having to do with the planet because all these have to do with planets. Good. So we need to connect a few mental pictures here. What does it mean, redshift, blue shift? Yeah,
Like back and forth.
back and forth. Okay, back and forth. So I'm seeing something move back and forth. And what happened in your Doppler shift when you're moving left and right? Sorry, so let's say just you. And if I'm moving this way, is there blue shift or red shift? No. Right? So if I move back and forth this way, there's no shift. Right? But now if I move this way, this is blue towards you and red, or vice versa. Right? Okay. So what if I go around in a circle? Say that out louder.
That's it. That's it.
Okay, now everyone's seeing it slightly differently, so your timing might have been different from, but what we're talking about here is something is orbiting. Okay, planets. Okay, now we've connected it. Okay, period of 16 months. What does that mean? Yeah.
Oh, that's how long it takes for it to go around the star?
Okay, that's how long it takes for us to go around the star. How long do we take to go around our star? 12 months. We do know that. Good. Is this bigger or smaller?
Bigger.
This is larger than 12. Good. So if we orbit, if we're on this planet, we orbit closer or farther than the Earth? Farther. Why farther? What's that? The orbit's bigger. Yeah. So recall that as we get closer to the sun, the orbits get small and we move faster. Right? So our time to go around goes quickly. If I'm very far away, let's say I'm Mars. Mars is only 1.5 times as far, and yet it takes almost 2 years to go around the sun. Okay. So put all of those pieces together. Does it have anything to do with mass? So which one of these is right? What'd you say? B. Because it's orbiting at a distance greater than us. Right? Okay, so now we can do this, right? We're 100% ready for the exam?
No.
All right, we'll come back to it. We're gonna do a lot of it. Okay, so this is that thing that I just showed you with my hands. the star is being tugged by the planet, and the planet is being tugged by the star. So they're mutually going around one another. And as it comes towards us, it shifts the blue light, and as it moves away, it shifts the red light. Right? Okay. So really good techniques can measure walking speed. They're remarkable. 1 meter per second can tell the Doppler shift. That's surprising. That's surprising, right? What's an example of Doppler that you see in your day-to-day that you actually don't look forward to?
Voice home.
No.
Traffic.
What's that? Traffic. So there's something about traffic there, something about cars. How does a cop, they point a gun at you, not the actual gun, different gun. They point a gun at you and they give you a ticket for going 65. How did they get that? How did they figure that out? How did they figure that out? They didn't take the light from you, right? And then look at the spectral lines, no. But they used Doppler shift. They sent out a radar, they watched it come back, shift it. Isn't that interesting? Yeah, I mean, it sucks. No one likes getting a ticket. Happens to everyone, right? Okay. So if we go backwards now, we're gonna draw a picture. Okay. And what I want you to think about is this concept. Red, blue. Red, blue. Okay. And then we're going to convert it into towards us, away from us. And in particular, we're thinking about speed. So here, how is it moving towards us? Or away from us? Or neither? This part here. So it's going around like this. But this part here, is it moving towards us, away from us, or neither? We're down here. Okay, let's go this side. If you go here, as it moves here, is it moving towards us, away from us, or neither? Towards us. Okay. It goes here, towards us, away from us, or away from us. Right? And then here, neither. Good. So I got two neithers, one towards us, one away from us. Okay. All right. So that is this. Now what the hell is this? Okay. This is time. I'm watching night after night after night and taking measurements. Notice these are times in days, and this is speed. So sometimes it's towards us, positive. Sometimes it's away from us, negative. And then sometimes it's 0. So the star looks like it's speeding up, slowing down, speeding up, slowing down, right? Back and forth, back and forth. And if I look at this little curve, I can just say, oh, I know what its orbit is. I look at this peak, and I look at this peak, and I take the difference. That's how long it takes to go around its star once. Does that make sense? Questions about this? And now it's gonna get harder. Okay. What is the difference between 1 and 2? Is it that A, 1 has a more massive planet? B, 2 has a more massive planet? C, 1 has a closer planet? Sorry, D, 2 has a closer planet? Or E, 1 has a highly eccentric orbit? You know when you're ready to vote? Vote on 3, 2, 1. Okay, I've got almost every answer but this one. Folks didn't like this one, or why not? It's the best one, right? It's alone. It's not like the others. I gotta get better at those. Okay. Turn to your partner, ask them what their answer is. If you got the same answer, ask someone behind you or in front of you. Okay. Are we ready to revote? Come here, Fitz, if you're ready to revote. Let's vote on 3, 2, 1. Interesting. So lots of people said 1 has a closer planet. How do we get there? Yeah.
Because if it goes back and forth more often, I mean, it has a closer orbit.
Oh, right, because we were just talking about that other one with the 16-month orbit, right? That was farther away. Yeah, I like that. Anyone disagree with that? Yeah, that's the right one there. So we haven't talked about what the mass does on this picture yet. What we showed here, that when we look at the peaks, they're close, moving around more quickly, right? Okay, what about this one? What's going on at 4? Is it a very massive planet? A very close planet? A very far planet? A very eccentric planet? And note, this is all real data. These are the names of the planets, and this is the real light curves. Show me your fist when you're ready to vote. Let's vote on 3, 2, 1. Okay, so people answered all answer the same. Interesting. What is this one? How would you read it? So it's got a really big change here, right? And it spends a long time out here doing nothing, essentially. Then it looks like it comes diving back down, and then it switches again. What would this behavior look like? Well, spends a short amount of time here, long period of time out there. So if I had a, say, a planet, and the ball, I have a planet and the star, and the planet's coming close. It's way out here, it's usually moving very slowly, and it picks up speed as it gets closer. As it gets really close, it picks up a lot of speed. Similarly, the star picks up a lot of speed in that time period. But for a short amount of time, it picks up a lot of speed, and then it goes off in the other direction very quickly. It's shot out the other side, and the planet just sits at the other direction. This is a very highly eccentric planet. Okay. 4, a very eccentric planet. Okay. So you can look at this and you can tell a lot of cool things. You can say small orbit, that was correct. Highly eccentric orbit, that was correct. You have large orbits, so the peaks are far apart. And then if they're really big, then they pull on the star more. With small, you won't really see that change. Big change, you have a big planet. Right? Questions about this? Basically, have 3 knobs to play with. You have distance, mass, your eccentricity. Okay. And then you have multiple planets. And this is real data too. So what you do is you have an undergrad or grad student have to try and fit that. So I did in undergrad. It's pretty fun. It's just little ups and downs. And you just go in there and you play with some knobs and you find out that there's 2 planets here. Okay. So up here you have planet C with this period and planet D with that period. And you can find out everything you want about them. They're both eccentric. They're both tilted funny. Yeah, real deal. What? That's the speed. That's the amplitude of the speed. How quickly they're moving. 15 meters per second. How much they're pulling on their star. Okay. I won't make you do multiple planets with us. Just when you come to work, right? Okay. All right. So we've talked about direct detection, seeing the actual planet. We talked about indirect detection, which is due to the mass of the planet. We just talked about the entire Doppler technique, and we're going to talk about the size of the planet. And once we have the size of the planet, we'll have all the things we need in order to understand what other planets in the universe might look like. Okay. So this is the first exoplanet to be detected. That's not a real picture. Right? This one here, 51 Pegasus B is named after the star. Okay, so 51 Pegasus is the star, and this is the planet B. Okay. All right, you can tell I made this one. Okay. Which one of these represents my hand passing in front of a candle? Is this time again? But now this is brightness. And this is supposed to be flat. This one is supposed to go down. This one has a little hump in it, and this one has 2 little humps there going up to the right. And if you want to practice this, you can imagine that you're looking at a candle and you're doing this calculation. Okay? You're doing the photometry, okay? When you're ready. Okay, let's vote on 3, 2, 1. Okay. Most folks agreed. Want to say what they chose? Why do y'all choose C? Yeah. So my hand's over here and I'm looking at the light. It's like fully bright. When I do this, I have less brightness, but it's not suddenly dark. And then I move that and then I can see again. Amazing. What a great demonstration. Okay, so here's what we're seeing in the data. So this is called the transit technique. This is what happens when a planet crosses in front of a star. Or interestingly enough, so here in the front, this is the one that we just thought about. Planet passing in front of the star. But then when you get to this orientation, okay, let's say you're all the star, or you're all the observer, I'm the star. So now I'm bouncing light off of my hand towards you. But then what if it passes in front of me? Then I can't see the planet and it goes down a second time. This is real data on the left and on the right. This one's bigger, obviously. When you block out the star's light, it's much more important than when you block out the planet's light. Okay. This shape here, this little shape you do, tells us how big it is. Is that obvious? Okay, so this is roughly my face shaped, right? As it passes in front of my face, if you can't see my face, they must be the same size, right? Pretty cool, huh? So we can just directly tell how large something is based on how much of the light you can continue to see. If it's really, really deep, it's a massive planet. Usually they're very small. Okay, because planets are very small compared to other stars. Okay. You already had the mass, assuming that you see it moving away and towards you. Now I have the radius. What does that give us? What's that? Mass, radius. Imagine that I'm going to the doctor and I tell them I'm, 7 feet and 350 pounds. They would say, "You're large." Yeah, very good. What if they said, okay, what if I said I'm 4 foot tall and I'm 390 pounds? What was that? Obese. What is that a measure of? In scientific terms, density. How much of you, like, what if I was like just absolutely jacked as a 4-footer, right? Right? I could be like super muscular. You assumed that I was fat, but if you look at that measurement, right? It's how much of something is in it. And we use this actually when we're looking at gas giants, right? Because the density, for example, of Jupiter is less than water. Whereas the density of the Earth is greater or less than water? Greater. It must be because we're standing on it, right? It's roughly the density of, anyone remember? What's the density of the Earth roughly? Not in numbers, but in words. Is it ice? Rocks, yeah, rocky metals. Okay. So if we know the density of an object, we can actually tell a tremendous amount about it. Okay. So before we get into like Kepler and doing all the rest of this, I don't know if we'll have lots of time. I guess we could kind of go through it. Here's 3 minutes. 2 things. So 1, we have an observing night tonight. And then 2, some folks have still not been doing the homework. It will be really hard to do all of the homework at the very end of the class and also pass the class. Right? So let me know what's going on. If you need help, if you want to talk about it. Okay? Okay. Okay, thanks, folks. Sorry, that was a bad note to leave on. But the observing night is also tonight, so that's fun. If there's no clouds, yeah, again, if you can see the sky and the lights are on, we're there. If you have any questions, you can obviously send me either an email or a Slack chat. That again? Yeah, totally. Thank you. Why wouldn't it be straight? So for example, okay, ready? Watch this. So this is bright, right? If my hand goes in front of it, it's now dark because the thing that's giving off the light. So like stand here, stand on this side, right? So right here, it's very bright. It's in my eyes, very annoying. As my hand goes in front of it, it's still quite bright. I can still see a lot of light, but then as it goes away, you see the shadow? Yeah. So that means it's going down a little bit, the total light. Does that make sense?
Yeah, and for the observatory, can we get there at 6?
Yeah, that's okay.
Oh, I just have a question. Of the
Yeah.
observatory report, because the first one I sent you, I sent you with the email, like in the Google Docs.
Okay, and then, did I?
Is there another way, like, that I had to send you that?
No, just remind me. Sometimes what happens is that I'm bad at life and I lose emails.